Hello, this talk is about combinatorial group testing and sparse recovery schemes with near-optimal decoding time. I am Vasileios Nakos, and this joint work with Mahdi Cheraghchi. So, there's a population of size n, and there are k individuals inside the population who are infected with the virus. The goal is to detect them using queries of the form, does a set S subset of n contain an infected individual? Formally, you can access a vector x, which is a 0-1 vector of length n and has at most k ones, using m non-adaptive disjunctive measurements of the form logical or overall line S of xi for sets S subset of n of your choice. And the goal is to recover x, which is k-sparse, or which will be called k-sparse, with a minimum number of measurements / queries. So for k equals 1, this is a very well-known problem. Most of you might have seen it, and this can be done using log n measurements. If you write this problem in matrix notation, y equals mx, each row of m corresponds to a choice of a set S. And here you should think as working over the algebra bool. So m is essentially the collection of all the tests. Each row corresponds to a test. And the inner product of a row of m and x gives us the outcome of the test on the population. So y is essentially the collection of all the outcomes of the tests. And so the goal is to minimize m, which is the number of tests and also the number of rows of m. Note that capital M, matrix capital M, is a small m by small n matrix, as well minimize the time to recover x, which will be called the decoding time, given y. So this problem is a very old problem. It was introduced by Dorfman in 1943 in the context of testing syphilis-infected soldiers. And it has apparently regained interest during the COVID pandemic. And this illustration here, this image, I took it from Wikipedia, and it's something called multiplex assay design. It was designed during COVID-19, during this summer, apparently, or this March. I cannot claim I understand how it works, but you can check Wikipedia for a nice fact and a nice application of group testing. Now let's see a related problem, which is called heavy hitters. You're given a vector x in Rn, initialized to the all zeros vector, and a long stream of updates I, delta, causing increment of xi by delta. The goal is to maintain a low space data structure, which upon query finds all the I in n such that xi is at least 1 over k times del 1 norm of x. And as you can see, there can be at most k of those elements. So there's an analogy there's an immediate analogy to group testing. The Foxner paper in this work will be the so-called strict style model, in which at all query points, xi will be at least 0. And the goals will be to minimize space and query update time. The strict style model is one of the most common models for the heavy hitters problem. And the heavy hitters problem itself is one of the most classical streaming problems, with applications in internet routing, traffic monitoring, etc. Now let's see yet another related problem, which is called compressed sensing. This problem originates in signal processing, and the goal is to design a linear sketch F, which is an m by n matrix with real entries, so that given y equals phi x with x in Rn, we can recover the best case sparse approximation to x in an L2 sense. This means, morally, we want to recover most of the k largest in magnitude coordinates of x. This is not precisely correct, but for the sake of this slide, you can think it like this. And now you can see there's an immediate analogy to group testing. You have an x which is a k-sparse vector. Now it's not a 0-1 vector, it's an arbitrary vector. It has real coefficients, maybe even complex. And you want to design a matrix phi so that given y, which is phi times x, you want to recover x if it's k-sparse, or the top k coordinates in x in an L2 sense. And the goal is to minimize m and the recover decoding time. Okay. Now, all these problems can be put under the umbrella of sparse recovery. What's that? this is essentially a field of computer science which aims at recovering k-sparse vectors using queries/measurements from a restricted class. So group testing corresponds to the disjunctive measurements. That is, you choose a subset S of n, and you take the logical OR of all the elements in the subset. Heavy hitters correspond to linear measurements, and there's an asterisk there because all the low space data structures we know for heavy hitters in the strict style model are essentially linear sketches. This means they're linear transformations. And 3 compression corresponds also to linear measurements. And what we're going to see in this talk, we saw that the connection is not only intuitive, and we provide a new method for designing near optimal decoders for all 3 of those aforementioned tasks, based on efficiently decodable group testing. Our focus mainly on the technical level will be group testing in this talk, but we will also briefly talk about heavy hitters and compression. Okay. Now let's see what are disjunct and least disjunct matrices. So let me say what disjunct matrix is useful about. So a k-disjunct matrix allows us to find a k-sparse x given y equals mx, where m is the matrix. And this holds for any x. This is a for all guarantee. Whichever x you give me, for every x, if you observe m times x, you can recover x. Now, k, least disjunct matrices are a relaxed notion of disjunct matrices, and they are the following. They are matrices m by n, 0, 1, so that given y equals mx in algebra bool, for a k-sparse x, we can find a set L of size k plus L, which contains every 1 in x. That said, least disjunct matrices allow outputting a small number of false positives, that is L false positives, apart from x. Good. So now let me go with the combinatorial definition of disjunct matrices. For every k plus 1 distinct columns, mi star, mi1, mi2, up to mik of m, if you interpret these columns as sets, because this is a 0, 1 matrix, so you can interpret every column as the indicator vector of a set, then it holds that mi star is not a subset of mi1 union mi2 union mik. In words, for every I star and every I1 to ik, different than I star, there exists a test J such that among I star and I1, I2, ik, only I star participates in. So this combinatorial definition immediately gives a naive decoder for disjunct matrices. I iterate overall I in n and discard I if it belongs to a negative test. This decoder runs in time at least linear in n, so it's not sublinear in n, it's linear in n. And with a moment's thought, you can be persuaded that it returns exactly the support of x, that is, all the ones in x, all the position where x has 1. Every other position, every other I in n will be discarded. And there's a similar definition for least disjunct matrices, but I won't give it in this talk. So what are the combinatorial bounds? No. Now, so far I'm talking about decoders that take linear in n time. So for k-disjunct matrices, we have an upper bound of the number of rows, which is roughly k squared, and the lower bound, which is again roughly k squared. There's some discrepancy between the lower bound and the upper bound, and this is a long-standing open problem in the area. But up to that small logarithmic discrepancy, roughly log n, or log base k of n, the quadratic dependence is correct. Okay, so for the interesting thing with k, of k least disjunct matrices is that one can shave off a factor of k from the number of rows with, in comparison to k disjunct matrices. So one has k log n over k number of rows, and this is optimal. So if one allows up to a small number of false positives, you can get rid of, you can turn this k squared factor to k. And also there's the non-uniform group testing, which is the following. It's a probability distribution over matrices sufficing to recover a fixed x with constant probability. So while disjunct and list-disjunct matrices hold in the for all x, allows you to recover every x, non-uniform group testing allows you to recover a fixed x with constant probability. And in that case, the upper bound on the number of rows is k log n. So what will be interesting in this talk is sublinear-time decoders. And what we're going to show in this talk is that previous trade-offs between the number of measurements and the decoding time can be greatly improved. So for k disjunct matrices, the number of measurements, which is the best known, is this fancy term with quadratic dependence of k on k. And the previous time bounds were k squared per log n. We saw that we can make this time bound number of measurements. For k of k least disjunct matrices, there were two available results in the literature, roughly speaking. One got k log n over k times a slight suboptimality, a log n factor, but got k squared decoding time, and the other got k log squared n over k, number of measurements, a log factor worse than the optimal, and got k log squared n over k decoding time. Our work shows that you can get the optimal number of measurements with only a log n over k factor slope down. And also for non-uniform group testing, the number of measurements in the literature was k log n, the fast algorithm was k squared log n, and our time bounds are k log n. So furthermore, this is only the tip of the iceberg, this is not the start. We saw faster error correcting variants of group testing, a faster decoder for heavy hitters, for two variants of heavy hitters, an explicit construction of disjunct matrices, a faster decoder for compressed sensing, etc., etc. And what we do so by bringing to the table a new sparse recovery framework. So our starting point and one of the strongest tools in this work is the following theorem. There exists a randomized construction of a k, O of k log n over k least disjunct matrix with an optimal number of rows and with an optimal type decoder. So what does it say is that, look, if you are fine in finding a list L that contains up to O of k log n over k false positives, then you can get away with an optimal number of rows and with an optimal time decoder. And now, with this theorem in hand, the procedure is kind of the road ahead is kind of natural. You vertically stack another least disjunct matrix or another disjunct matrix with possibly an inefficient decoder. And after getting L, you just run the naive decoder only for elements in L. This means that you iterate over only elements in L and check whether they're defected or not. So what essentially theorem does is performs a universe reduction. It takes you from universe of size n to universe of size O of k log n over k, where you have to run the naive decoder only on the latter universe. So this idea plus some additional work yields all the results in the previous slide. Then you can have an error correcting variant of the above, which means that an adversary might choose to destroy some of your measurements, turn the outcome of a measurement from false to true or from true to false, from 0 to 1, from 1 to 0. And so you want to protect yourself against that. And then we provide an error correcting variant of this theorem and then use some new and some old tricks to yield results for heavy hitters and error correcting group testing. And a more ad hoc argument then can be used to get improved compressed sensing. The argument is a bit different. You cannot put it exactly in the same framework, but in principle it's very closely related to this theorem. Okay, and now let me go to the proof of the starting point. Which the rest of the talk will be devoted. So the idea is to learn the bits of all defective items one by one. So for a number x, we define the binary prefix of x at length L to be the string that has the first L digits in the binary representation of x. So in this setting, this is our x. And binary prefix of x at length 4 equals this string here, which is 0101. So what's the idea now? That is the following. For a specific length L, we hash the initial universe n's to OK buckets with the following constraint, that all I with the same b pref of L value are hashed to the same bucket. This means that if you have two strings I and I prime, and such that both b pref of L of I equals b pref of L of I prime equals 0101, for example, in this case, and they're going to be hashed to the same bucket. They're going to be hashed to the same bucket, which translates to the following thing, that look, what we're essentially doing, we are hashing only the prefixes. We're hashing a 2 to the L sized universe. We're not hashing n. So what we're essentially doing now, for all L, for all possible lengths L from log k to log n, we pick a hash function from 2 to the L to the interval c times k. So we hash 2 to the L to c times k buckets. And for all these values, and for each bucket, we perform a test. We say, look, all the guys, all the elements that fall in bucket B, we take them and we create a test, we create a measurement. This is essentially all the buckets, all the elements that fall in bucket B for a fixed L. Okay, and how much, what's the number of measurements? The number of measurements, just C times K times log n minus log K plus 1, which is O of K log n over K, this soft one. Okay, this sounds very simple, and it is indeed quite simple. And how do we decode in just straight? And now the question to answer is the following. How do you decode from those measurements? And the approach is very natural, something like DFS with some sort of pruning. So you keep sets SL such that each set SL is a small set of length L strings, such that for every defective item X, there exists an element in a cell which is a prefix of X. So roughly speaking, SL at all points contain prefixes, length L prefixes of all defective items, of the binary representations of all defective items. So you start at you're starting by adding all log k bit strings, and then you proceed for all L in log k, log n minus 1. For every X in SL, you just add two possibilities. You add 0 and 1 to create two new elements. And then you test for every element if it participates in a false measurement, in a negative test. That's it. And at the end, you output the last set, which definitely contains all defective items. And the whole thing is just to bound this process, to say that, look, S log n is small, and not only S log n is small, but the running time of this process is small, meaning that the total size of all sets S is small. What small means O of k log n over k. And so if you do this, if you bound the number of all X that were ever inserted in some set, SL, then you immediately get a bound on the size of the last set, which corresponds to the list L, to the list L of defect items that your algorithm outputs. Good, and now let's see what's the proof. The claim, for some choice of the hash functions, O of k log n over k elements will ever be inserted in any SL, hence the running time, and the bound of the size of the output list. Okay, now the argument is again very compact. Let's count the probability that more than, let's fix actually a set X, a vector, and what's the probability that more than O of k log n over k elements ever insert in some S? This is, if you think a bit about it, this is something like 1 over C times O of k log n over k. this kind of branching process. And now what you have to do, you have to count the number of possible trajectories the algorithm could evolve. And because if you think a bit about it, this algorithm creates a binary tree. The number of possible trajectories the algorithm could evolve is n choose k times the Catalan numbers of k log n over k squared, which is 2 to the o of k log n over k. By choosing c large enough, this allows you to take a union bound over all possible supports and overall possible trajectories the algorithm would evolve. And that's it. That's the proof of the starting point. I've hidden some details, but you can go look at the full version of the paper. The proof is less than 1.5 pages. And now what's the bottom line? Once you have this, you optimize the starting point idea by adding error correction and then by adapting it to the compressed sensing world, where things are much more complicated, but fortunately it can be done. Then once you have optimized the starting point idea with error correction, you start putting all the bits together and get error correcting group testing schemes. You get an explicit construction of group testing matrices, you get heavy hitters, two results of heavy hitters, so on and so forth. So numerous new consequences follow once you have this. And then with some work, you can get, as I said, some near optimal results for well-studied problems. The result for compressed sensing is much more complicated than the other part, but still, the bottom line is this simple starting point idea can give you many new consequences. And in some sense, we have introduced a new sparse recovery framework. You find a small list containing all defective items or all relevant items if you are in the heavy hitters of the compressed sensing world, and then you continue from there to recover everything else. And there are other sparse recovery problems which await the resolution, many cool things happening in this area. And I hope you enjoyed the talk. Thank you.